Hi everyone, this is John. Today I'm going to be walking through how to prove whether arguments in English are true or not using concepts of natural deduction. So to get started with the first one, we have everyone enrolled in the university has lived in a dormitory. Mia has never lived in a dormitory. Therefore, Mia is not enrolled in the university. So I'm going to go through this step by step and kind of break down each sentence one at a time. So our goal is to translate this into logical expressions. So looking at the first sentence, we can immediately see that there is this everyone here. So we can tell that this is eventually going to get translated into some sort of quantifier. And we're going to want to use the universal quantifier because we're quantifying everyone in our domain. So everyone enrolled in the university has lived in a dormitory. So we can see that there are two different statements here about these people that we're describing. We have enrolled in the university and we have has lived in a dormitory. So I've written down these two predicates here, u of x and d of x, to describe these statements. So u of x is enrolled in the university, and d of x is x has lived in a dormitory. And the reason that we want these to be predicates is because we want to be able to have different truth values for different objects in our domain. All right, so translating this first English sentence into a logical expression, we have everyone. So this is going to be our universal quantifier for all x. So everyone enrolled in the university, that's our u of x. Now I'm going to choose to use the implication arrow here, and I'll explain why I chose the implication here. So everyone enrolled in the university has lived in a dormitory, which is our d of x. So suppose instead of using the implication, the only other choice we would really have here is the and connective. So what if we did use and? Well, what is this saying? So this is saying that for all x, u of x and d of x are true, or in other words, everyone has enrolled in the university and everyone has lived in a dormitory. But this isn't really what we want to say because this definitely isn't true for everyone. What we want to say is that if you've lived in the university, then you definitely live in a dormitory. So another way that I like to think about this is we're restricting the set of everyone to a specific subset of those people. And that subset is the people who have enrolled in the university. So this premise here is restricting our domain to a certain set of people who have enrolled in the university. Okay, so that's one premise. Again, our goal is to translate this into logical expressions so that we can use natural deduction to justify whether this is correct or not. Moving on, we have that Mia has never lived in a dormitory. Now this corresponds to d of x. So we can negate that to get the never, and we want to plug in Mia for x because we are describing Mia. So this is another premise. Finally, we want to be able to conclude somewhere down the line that Mia is not enrolled in the university. Using our predicates, this is not u of Mia. So this is what we want our conclusion to be. So we have this for all statement, but we want to be able to work with predicates involving Mia. So what we can do is use for all a lim, which basically says if we know that something is true for all x, then we can definitely say it's true for a very specific x. And that specific x here is going to be Mia because we are dealing with Mia. So we can use for all a lim to say that u of Mia implies d of Mia. And this is for all lim with line 1. And from here, we are actually done because we can justify this conclusion using modus tollens. Now, this isn't a specific rule with natural deduction that we have to use, but we can definitely prove it. So modus tollens tells us that if we have this implication, U of Mia implies D of Mia, and we have the negation of the conclusion, or D of Mia, the negation of D of Mia, then we can conclude the negation of the premise, or the negation of U of Mia. Now, intuitively, I like to think of this as utilizing the fact that the contrapositive is logically equivalent to an implication. So really, we're turning this U of Mia implies D of Mia into the contrapositive, and then implicitly using the implication elimination to get our negation of U. And again, you can prove this on your own using another natural deduction proof, but I won't go through that here. So we have shown that this is true using natural deduction. All right, moving on. Another set of arguments. So we have a convertible car is fun to drive. Isaac's car is not a convertible. Therefore, Isaac's car is not fun to drive. So based off of these 3 sentences, we can tell that the objects that we're wanting to quantify here are cars. So our domain of discourse is going to be cars here. And we can tell that there are 2 different things that we can say about cars based on these sentences here. And we're going to decode them into predicates, again, like last time. So I'm going to start with the second sentence to see this, but the second sentence says Isaac's car is not a convertible. So we have some sort of statement that says whether a car is a convertible or not. So I use this C of X to describe that. And also we have this statement that a car is not fun to drive. So this F of X is describing whether a car is fun to drive or not. So C of X is a convertible. F of X is fun to drive. So going through these sentences, a convertible car is fun to drive. So every car that is a convertible is fun to drive. C of X is a convertible. F of X is fun to drive. Again, you can reason through why we're using the implication here, like I did last time. This is a premise. Isaac's car is not a convertible. We're saying something about a very specific car. So not a convertible, that's the negation of C. And we're doing that for Isaac's car. And we want to eventually show that Isaac's car is not fun to drive, or the negation of F with Isaac's car plugged in. Okay, again, we can use for all a limb. Same idea as last time. We want to do it for the specific car that we're considering here, or Isaac's car. This is for all limb on line 1. Okay. So we have this implication, C of Isaac's car implies F of Isaac's car, and we have the negation of C of Isaac's car. So can we get the negation of F of Isaac's car from this? Now, to see this, I'm going to use a truth table to kind of reason about why this isn't the case, that we can show that the negation of F of Isaac's car is true. So if you imagine that P is C of X here, and Q is F of X. So we have that P is false. So we're working with these two rows, and C implies F is true. So these are the two rows that we're considering. We want to be able to say something about Q. But as we can see, in these two cases, Q is both true and false. So there's not really anything that we can conclude about Q, because it could be the case that Q is either true or false. So it doesn't make sense to conclude that the negation of F is true, because it could be the case that either F is true or the negation of F is true based on the information that we have. So from there, we can say that this is an incorrect argument. This is known as the fallacy of denying the hypothesis. Because we're negating the hypothesis of C of Isaac's car being true, and we're incorrectly concluding that the negation of the conclusion is true as well. All right. Next, we have Quincy likes all action movies. Quincy likes the movie 8 Men Out. Therefore, 8 Men Out is an action movie. I'm going to go through this one a bit quicker. So the first sentence translates to, for all X, if we have an action movie, then Quincy must like it. So this is using the predicates that I've defined here, A of X and Q of X. This is a premise. We have Quincy likes the movie 8 Men Out. So that's Q of 8 Men Out. I'm going to use EMO for short. Another premise. And we eventually want to show that 8 Men Out is an action movie, or A of 8 Men Out. Okay. Again, you should be getting pretty familiar with how to use for all and lim to our advantage here. So we want to instantiate A of X implies Q of X for 8 Men Out. All right. So we have Q of EMO. A of EMO implies Q of EMO. And we want to be able to conclude A of EMO. So again, I'm going to use the truth table to argue through this. So assuming that we let P equal A of X and Q equal Q of X, we have that Q is true. So we are in these two rows. And again, we want to be able to conclude whether P is true or false. Or sorry, our goal is to conclude that P is true because we have that A of EMO is true. But again, just like last time, if we look at these two cases, in the first one, P is true, but in the second one, P is false. So it could be the case that P is either true or false. Or in our case, A is either true or false. So again, it doesn't make any sense to conclude that A is true, given that it could be the case that it's either true or false. So again, this is an incorrect conclusion. This is known as the fallacy of affirming the conclusion. All right, last example here. We have all lobstermen set at least a dozen traps. Hamilton is a lobsterman. Therefore, Hamilton sets at least a dozen traps. So I've written the predicates L of x, where x is a lobster man, and T of x, x sets at least a dozen traps. So the first sentence translates into for all x. So if you are a lobster man, L of x, then you set at least a dozen traps. So all lobster men set at least a dozen traps. Hamilton is a lobster man. So L is true when you plug in Hamilton. Okay. And we want to conclude that Hamilton sets at least a dozen traps, or T of Hamilton. Okay. Again, we're going to want to instantiate this for Hamilton using for all a limb on line 1. Now here we can see that we have the direct application of the implication elimination just on what we have here. So we have L of Hamilton, and we have L of Hamilton implies T of Hamilton. So with a direct application of the implication elimination on lines 2 and 3, we can conclude that T of Hamilton is true. All right, and that wraps up justifying English arguments using concepts of natural deduction.